In this rather longer tidbit, so less of a tidbit, more of a tid section, we're going to derive the second, or the n equals 2 Chebychev polynomial using the second solution formula. This video will directly answer question 2 part 3 of the Mathematical Methods for Physics 21/22 exam as taught by the Department of Physics and Astronomy at the University of Manchester. With the question being part 3, there are some things that would be useful to know beforehand. Throughout the question, we'll be using polynomials big U n of x, but the only polynomial that we actually need to know to solve this question is u1 of x, which is equal to 2x, which would have been derived in a previous question. Otherwise, the rest of the solution does not rely on any former knowledge of the questions. In the question, we're told that some functions little u of x is equal to square root 1 minus x squared, big U n of x, satisfies the differential equation 1 minus x squared d squared u by dx squared minus x du by dx plus n plus 1 squared u of x is equal to 0. In addition to this, we're also told that there are additional solutions to this differential equation, which are the Chebychev polynomials t n plus 1 of x. Immediately, this tells us that the Chebychev polynomials Tn of x must be proportional to, at least, the solutions little u of x for n minus 1, i.e. it's proportional to square root 1 minus x squared u n of x, n minus 1 of x, sorry. Now, to find the Chebychev polynomials Tn of x, we can use the second solution formulae. For an already known function y1 and a function y2 that we wish to find, we know that y2 of x is equal to y1 of x multiplied by the integral 2x of e to the minus integral to x primed pz dz divided by y1 squared of x, and this is over dx primed. In this case, we can take our y1 of x to be root 1 minus x squared un minus 1x. This is because we know from earlier that big U, little u, sorry, satisfied the differential equation, as did the Tn plus 1 Chebychev polynomials. The p in the second solution formula comes from the differential equation y prime primed plus p y primed plus qy is equal to 0, which we can get from inspecting the differential equation from before. If we divide the differential equation through by 1 minus x squared, we get u prime primed minus x over 1 minus x squared u primed plus n plus 1 squared over 1 minus x squared u is equal to 0, where in this instance primes are denoting derivatives with respect to x, but that's not the same as the prime used on the x's in the integral. So we can see that p is equal to minus x over 1 minus x squared. So to begin, we will compute the numerator in the integrand, which is e to the minus integral to x primed pz dz. So we will compute the integral to x primed minus x over 1 minus x squared, or I'll leave this in terms of z actually. Z over 1 minus z squared dz. One thing we can note about this equation, or this integral even, is that the derivative of the bottom would be minus 2z. Therefore, if we keep the negative sign on the numerator of the integrand, we can see that the numerator is a half the derivative of the denominator. Therefore, if we multiply the numerator by 2 and divide the whole integrand by a half, we don't change the value of the integral, but we do put it into a form whereby we have an integral of the form f prime z over f of z dz. And this is a standard integral with the solution ln mod f of z. I just need to put in some missing negative signs that I'd forgotten there. So we know that this will be equal to minus a half ln mod 1 minus z squared. And equally, we can bring the half over into the log to get ln of mod 1 minus z squared to the minus half. Equally, we can see that when we now plug this back into here and perform the change of variable to x prime as given in the integral, the result, the exponential of minus the integral blah 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 blah, will give us just 1 minus x primed squared to the minus half. We can now plug this into the rest of our formula for the second solution, and we will get Tn of x is proportional to square root 1 minus x squared u n minus 1 of x. The integral to x of 1 minus x primed squared is minus half square root 1 minus x squared u n minus 1 x squared dx primed prime. And finally, this gives us root 1 minus x squared u n minus 1 x integral to x of 1 over 1 minus x prime squared to the 3 over 2 u n minus 1 x primed squared dx primed. Now all that's left to work out is the integral here. So we will ask, what is the integral of 1 over 1 minus x primed squared to 3 over 2 u n minus 1 squared of x primed dx primed. And it may be useful to write out the denominator slightly differently as square root 1 minus x primed squared cubed u n minus 1 squared x primed, just because it's easy to see what's going on here. Now, for the specific case where we want to find out t2, the second, the n equals 1 Chebychev polynomial, we know that we will require the polynomial u n minus 1, which is u1, which we had earlier as 2x. So our integral is 1 over square root 1 minus x squared, x primed squared cubed 2x squared, which is just 4x primed squared dx primed. We can solve this with the substitution x primed is equal to sine theta. This gives us that dx primed is equal to cos theta d theta. Substituting this in, we get the integral of 1 over square root 1 minus sine squared theta cubed 4 sine squared theta multiplied by cos theta d theta. We know that from cos squared theta plus sine squared theta equals to 1, that 1 minus sine squared theta is equal to cos squared theta, so therefore the square root is just equal to cos theta, which we can then substitute in, and dividing by the cos theta on the numerator, we simply just get cos squared theta sine squared theta multiplied by 4 d theta. Next we can use the relation that sine 2 theta is equal to 2 sine squared theta cos squared theta, and we can now see that the denominator is just the square of this, so we can actually just rewrite the integral as the integral over x, 2x d theta over sine squared 2 theta, and this is simply equal to the integral of cosec 2 theta d theta, which is a standard integral, and this is equal to minus cot 2 theta plus c. I'm not going to substitute in the x just yet because I didn't change the limits on the integral earlier, so we will need to convert back to x primed and then substitute the x primed for x. So technically we should have written x equals x primed. Now, cot is equal to 1 over tan, and tan is equal to sine over cos, so we can write cot 2 theta, or minus cot 2 theta, as cos 2 theta divided by sine 2 theta. Using the double angle formulae, we have cos 2 theta is equal to 1 minus 2 sine squared theta, and sine 2 theta equals 2 sine theta cos theta as before. We can now write this as minus 1 minus 2 sine squared theta divided by 2 sine theta cos theta. Equally, we want to remove all cos theta terms and get the entire expression in terms of sine theta so that we can substitute back in x primed equals 2 sine theta. And as before, we knew that cos theta was equal to the square root of 1 minus sine squared theta, so we shall substitute that back in. So we get minus 1 minus 2 sine squared theta divided by 2 sine theta square root 1 minus sine squared theta plus c. And now we can substitute back in x primed is equal to sine theta is equal to x, and this gives us minus 1 minus 2x squared divided by 2x square root 1 minus x squared plus c, the result of our integral. All that's left is to multiply this by the original function y1, which is just square root 1 minus x squared un minus 1x, where un minus 1x was equal to 2x. So our second Chebychev polynomial, t2 of x, will be proportional to square root 1 minus x squared times 2x times minus 1 minus 2x squared divided by 2x square root 1 minus x squared plus c. Equally, we know that t2 of 1 is equal to 1, which allows us to find c. Writing this out, we have that t2 of x will be proportional to, and in this case because we have the integrating factor c, equal to this term all simplified down. We can see that the square root 1 minus x 2x is the same as the denominator over here, so we can cancel those out and we're left with minus 1 minus 2x squared plus c over square root 1 minus x squared 2x. From t2 of 1 is equal to 1, we can show that c is equal to 0, which finally leaves us with the answer t2 of x is equal to 2x squared minus 1, which is the final answer.